as we continue our discussion on line integrals, we're going to kind of try to visualize what they mean. And in this example, we'll visualize what we are actually calculating. So before we do an example, again, what do line integrals mean? Well, if our function represents density, then the line integral of that function with respect to arc length is the mass of a thin wire maybe shaped like that curve. Or if f of xy is a solid or a curve, then the area underneath the curve is found by taking the line integral. And so what does this kind of mean in space? Because we're going to do an example sort of like this here in a second. So we've got a curve down here in our xy plane. Here's my curve. And then potentially I have some surface. So there's my f of xy. All right, down here I've got my curve C. Essentially what we're doing is we are mapping that curve up to the surface here. And so we've got this wavy plane in a sense, and that's the area of this piece that we mapped from the curve up to that surface or solid. We've now used the line integral to find the area of essentially this, we could think about it as a wall. All right, let's look at an example. In this example, we're going to find the area of one side of this wall, which is standing up orthogonally or just perpendicular on this curve. So my curve is 2x plus 3y equals 6, which is just a line. And the line exists between x equals 0 and x equals 6. So beneath, we're drawing a wall from this line up to the surface, and we're finding the area of that wall we create. And my surface is defined as this plane, 4 plus 3x plus 2y. So what are our steps? Well, the first thing we need is we need this curve as a smooth parametrization. So let's think about how to parametrize 2x plus 3y equals 6. Well, we can say if x equals t, then what is my y value going to equal? So 2t plus 3y equals 6. We get 3y equals 6 minus 2t, or y equals 2 minus 2/3 t. So if x equals t, y equals 2 minus 2/3 t. And then c can be written as r of t equals ti plus 2 minus 2/3 tj. Or you could even write it t2 minus 2/3 t. And since x is equal to t, t is defined still from 0 to 6. So the second thing we would need would be ds. Okay, so ds is going to be the sum of the derivatives squared. So the derivative of t, we would have 1 squared plus my derivative right here, that's going to be negative 2/3. So I now have negative 2/3 squared. And then I have my dt at the end. So this is the square root of 1 plus 4/9, or the square root of 13/9, or root 13 over 3. So this is my extra factor I'm going to put in when I calculate my line integral. So my third step area is the line integral over c of that function f of xy ds. Or in this case, 0 to 6, 4 plus 3x plus 2y, and ds is root 13 over 3 dt. Now, we can't integrate this yet because we need everything in terms of t. So recall what x is. X is equal to t. Y is 2 minus 2/3 t. And this will now look like 0 to 6, 4 plus 3t plus 2 times 2 minus 2/3 t, root 13 over 3 dt. So we just need to make sure that we plug our parametric x and y into that original function. At this point, again, this is easy for us to integrate, so I'm going to encourage you to pause, make sure you can do that. I'm going to work it out. So working this out, I pull that constant in front. 4 plus 4 is 8. 3t minus 4/3 t, that's 9/3 minus 4/3 gives us 5/3. Integrate, we get 8t, 5 6t squared, plugging in 6, and 0, I don't need to evaluate 0 because that will 0 out. We end up with 26 root 13, and that represents the area on one side of this wall that we've created. So again, just reminding you, we have some curve or line down here in the XY plane, and then our surface somewhere up here in space, and we just mapped that wall up to that surface, and we found the area on one side of this wall. So that's it for this video. In the next video, we can talk about two paths. So maybe that curve is not just one piece, but we have two pieces that we need to consider. As always, email with any comments, questions, concerns, or just if you want to talk.